So this is a bit of the outline, what I'm going to be talking about today. It's going to be, why do we need levee upgrades? We all know the computers are upgraded, cars are upgraded, everything is upgraded nowadays, even our environmental regulations. So we have to follow that with geosynthetics or with the design as well. Then I'm going to explain a bit about the three-zone concept, which is an improvement for levees. And then I want to go the step beyond what I said. The young engineers, and also the ones who are still designing, to think about what else did I miss? Because water is smart. Water finds the weakness of everything. And we're dealing with water. And then, of course, sustainability. So a bit of what you hear from the others is going to be part of mine, but very short at the end, because I think that's covered pretty good. And then just do it right at the end of it. Let's start with our climate crisis. We heard a number right now from 1.5% degrees increase and insects dying. In my graphic, you see over here that if you look at, this is now for Germany, if you look at the temper period and if you look at these right columns over here, you see that the temperature is increasing every year. We know that. That's nothing new. I'm not here to explain that, why and how that's happening. And we have around about the last 50 or 100 years, we have around about this 1 degree. You can take the higher numbers, it will be 1.5 degrees, but that doesn't matter. Do you know the impact of 1 degree centigrade increase, what that really means? I was shocked as I heard that in a presentation several years ago. 1 degree's increase in temperature means for us here in Europe 10% more rain. Floods, water, rain, that fits together. And if we now go into 1.5 degrees or 2 degrees, it's going to be more water. The problem is we don't know where this water is coming down. It's evaporation. And we hear it every year. We had in Germany 3 years in a row huge dry summers. Okay, great. Warm, nice, sun. But then suddenly we had 2 years in a row where the water just flushed down the whole summer. And we had a lot of floods. We hear it this year in Italy. Next year, or last year before, it was in Spain, in Switzerland, in Austria. We always hear those dramatic rainfalls coming down. Over the year, it's not that much, but in a short period, it is. And this is basically what's happening over here. We're getting an increase of the events. And not only the short-time events, and that's the more dangerous part, is the long-term events. Having rainfalls for 72 hours, dramatic rain coming down. Everything we designed 100 years ago didn't include these factors. We didn't know about them. So please, young people, don't blame us. We did everything wrong. We didn't have the data for that. But now we have much more data, and now it's the chance to improve these things. So here we go. Here you see Southeast US. Same thing. You can see that the daily rainfall threshold values, the smaller rainfalls, they're decreasing. But those are the ones which concern us the most, where we get more rainfall in a shorter period of time. And that's going to influence us. And now my question, climate crisis meets an inequality or a structural imbalance. Not good design or levees not strong enough. What's the word for that? You were right, it shouldn't happen. But if it happens, what is that? It's easy. It's like with the egg of Columbus. If you have the answer, it's easy. It's a disaster or it's a tragedy. People die, we lose money, a lot of things happen. That's the consequence. We just have to face that. And now, as engineers, we have to go a step forward. These are 2002. Look at the levees. Levees were just flooded. They were not bad, they were not wrong, they were good designed, but they couldn't withhold the water for that period of time, because the period of time where water's coming down and flooding is longer than those levees were designed for. So we have to reconstruct these things. Many of those levees worldwide, not only in Germany, I think many parts of the world are old. How were they built? With sand. because that was good enough, because we knew it will have a flood, we'll have 2-3 days of water. Water cannot go through the dam. We don't have barriers in there. They just have to maintain the water and the pressure, and we're fine. So that was it. Now we have heavier rainfalls. We have more water coming down. And worst case scenario is we have rainfall and snow melt at the same time. We don't know when those things are going to happen. And if we have that, Austria had that, and Czechoslovakia and those countries, they had snow melt and then suddenly a lot of rain. That's a disaster for everybody. We also, as I mentioned, have longer and drier summers. What does that mean? That means the levees crack, roots grow deeper because they are looking for water. Animals bury themselves into those levees. They destroy them, make channels in there, and water, I said, is smart. That will find the way, go through there. And once the water goes through a dam, that's where we have the issue. And the last one, that's our problem. That's economics. The last one is our own problem. We're causing our own problem. We built too close to the levees. And I'll show you some examples. This is a good example because we had floodplains around in the area, and the farmer knew that, and he built a small levee around his property so nothing would happen because he knew flood would come, and he was safe. Now, of course, if it's not high enough, that's another issue. But that's a good design because the water from the floods can spread around in the floodplains. That's why we have them. You don't build into those, but in Australia, probably you're allowed to do that. This example, US, I'm sorry about that, but they followed the left reduction of floodplain areas. They said, oh, we have all this area over here, and we could sell it. Nothing happened the last 5 years. Let's make cheap land out of it. So you remove the levee closer to the river. You sell this, you build housing, and suddenly we have these rainfalls and snowmelt and whatsoever, and we have the floods, and everybody's surprised. And this is an example you see over here on the picture, is the original levee was back there. And now they built all the way to the front side, industrial area, fine, is great. Nothing happened to them, by the way. They were lucky because they lived upstream. But all this water coming down the river had to go somewhere. Originally, it was able to go into this floodplain area, but it's blocked. So the water just moves on down the river. And now the communities who lived down there, they got flooded. I can imagine in the US a lot of lawyers making a lot of money of that they're going to sue those people because it's their fault at their area, but that's another story. So don't do those things. The water has to go somewhere and has to go into the floodplains. So here we have the damage mechanisms of a levee. The first one, okay, we can't do anything against that one other than to build higher, is the overtopping. We'll come to all of those topics and how to build with geosynthetics and prevent those things to happen. Erosion on the upstream side, on the water side, critical because we can't see it. Because if the water's there, you don't see under the water what's happening there. If something like that happens, then your levee could burst and break. Seepage under the levee is also critical. You can see that because water would be on the downstream side, so you see that water if it's not raining. If it's rained the whole time in that area, you won't see it, but if it's dry and you're just having water, you can see those puddles of water. And then, of course, the seepage, which causes erosion on the backside, on the downstream side, which is really the big issue. So these are the things we have to consider in our design and do something against it. Now, the first and the easiest one, which every handbook will tell you, if you build a new dam, put a barrier on the front. Good. If you do that, I'm already happy, or every designer will be happy. You have a barrier on the front side. You're preventing the water flowing through your levee. You can go down on the front side. You can build horizontal there or vertical down here to prevent the underflow under the dam. Then you're already pretty good. But that would be, I would say, the easiest design. That's not the high-level first-class design, which I'm going to. The second thing we're going to be looking on is the supporting core, and the third one would be our release it's sometimes called, well, it's a permeable passive wedge. It's also called as a defense road, so roads and trucks can drive during the damaged or during the flood season in that area. So first of all, if we look at that, we have various solutions. Some of them are clay solutions, and can be geosynthetic solutions, and it can also be a geomembrane. Honestly speaking, geomembrane and compacted clay liners are those two solutions I would not 100% recommend in there, even though a geomembrane is probably, or it's not probably, but it's the most impermeable material we have. But you have to think in terms of construction as well. You have to weld them together on site. They have to be protected against damage. You need geosynthetics against or sand for protection. Sometimes you have structures there where you have to weld against, and you can't weld anything which is out of concrete and a geomembrane together, so you have a lot of costs involved in there. So geomembranes are not the most used ones. The most ones are basically geosynthetic clay liners, and we'll talk about these different systems just shortly. Now, I said I'm not going to talk about values, but I'm going to give you some recommendations what to think of. I want these young engineers to think a bit more. What do you do? First of all, you have to check if you have local requirements or not. Luckily, in Germany and also in the Netherlands, I'm not sure about US and all the other countries in the world, but I haven't seen very many. There's not many regulations out there which give you a guide. There are books, and they write about everything, but not too specifically about the geosynthetics. So check that number as number first. The second thing is, if you use a geosynthetic clay liner, most of them are going to tell you round about 4.9 kilogram, or let's say roughly 5 kilograms of bentonite is something you should have. Fine, that's good. That's a good number. It's a standard number. It's worldwide used. Doesn't matter if it's 4.5 kilograms or 5. I'm not taking that number over there. But sometimes it's wise to look at what is available on data. What do I have, basically? Is that a good number or not? Or can I go higher? Can I go lower? No, lower, don't go lower. But can I do more and better? And what does that basically mean? So if you take a GCL, for example, and you have 4 kilograms of bentonite, and you look at long-term values, you get a long-term value, you have to take a reduction factor, because the bentonite can, for example, undergo ionic exchange, and then it will have a higher permeability. So we have a factor, let's say roughly 10, just as a number. But if I increase my mass per unit area to 6 kilograms, as an example, and we know that from landfill design in Germany, suddenly your value, your improvement, or your not improvement, the other way around, your higher permeability value goes down to a factor of only 5. And if you now theoretically, which would be an overkill, if you go to 10 kilograms of bentonite as an example, which we also have seen on the market already, suddenly your values may be only by 2. Safety factor for the future. So that means your permeability in future is not going to be that low or not that high as you would have with a GCL with a low mass per unit area. So you can play with those numbers, just saying that. You can play with the geotextile components and the durability as well, but those are things you have to look on your own. I can't explain that in a half an hour. Next one is I can upgrade my GCL, as an example. I can put a polymer coating on top of it. This is like a composite lining system. We heard in landfills in the US, they only use composite lining systems or even double line systems. I mean, landfill is something else than a levee. On the other side, is it really something different? It doesn't have environmental impact, but it can impact properties and life, agriculture, everything of living around us. It can have a huge impact. So sometimes a good idea to think about how can I improve my system. It can't prevent roots growing through it, but it can minimize them going through. It can prevent desiccation. Bentonite, we all know, bentonite works with water, and if it dries out, it desiccates. But if there's a polymer coating or a geomembrane on top of it, I don't care, would be also fine for me. You won't have that desiccation anymore, and it will perform much, much better. Just as an idea, and of course, the last one, it improves the hydraulic conductivity. I think that's a no-brainer. We got that very easy. Now let's come to the extra points, how a good engineer should think. Now we heard that we had upstream slope failure because of erosion. There's a handbook chapter with erosion control in there where we have that. So now my point, which I say, where can the water really disturb or hurt my design? I covered the permeability, or the barrier. Now I have to look at the upstream surface. I know water's going to run down there. Water's going to run down fast. There can be trees and bushes in there, and they can take the weeds away. Once those roots and weeds from the grass are gone, it's a susceptible, dangerous situation, because now suddenly erosion can go very fast. So I can stop that by using geosynthetics, and I'm just saying the ones available. It can be erosion control method, it can be a nonwoven, it can be a composite material of a geogrid with a nonwoven together, and it can even be a geocontainer in that. And that's an example I want to show to you. If you really want to have a high-end design, and you know this could be a problem in future, or I want to avoid this future. Young people, think like this. If you build something like this, and after 10 years, this thing fails and 100 people die, 10 people die is enough, and you hear that, and you say, it was my design as a young engineer, you won't feel good. But if you say, hey, everything worked fine, because I put geocontainers in here with local sand. It's not expensive. I mean, maybe the construction is expensive, but taking local sand and just putting them in containers in front of that, and this is going to make my system safe for 50 or 100 years. Wow, I did a good job. You have to convince the people who have to pay for it, of course. But I think you can do that in analyses. The next thing is geogrid reinforcement on the base. Also, there's a chapter in the book. Why do I need a reinforcement down here? Why? Quick question, 3 seconds. One.
Slip circles.
Pardon me?
Slip circles.
Yeah, but what's the main reason for this?
Stabilization. Stabilization.
Stabilization, but okay, you're all on the right track. I need this over here to prevent that this part goes down 0.5 meter. Because if my top level at one point is 0.5 meter lower and I have a high water level at one time, that's where the water's going to go over it. And if I have overtopping in an area where I have settlement, your dam is damaged. You cannot stop it. Water running over a dam, no way to stop that. So this is a good idea. Yeah, you're correct. I want to prevent settlement. I want to have a stable ground. We're putting weight on weak soil. Yes, that's as well. But also the main thing is up here, I don't want my top, my crest, to settle just 5 centimeters down. The next thing is I want to have a very stable core. I want to prevent, in case anything happens, in case water flows through, in case my barrier didn't work, or if you don't build with a barrier, this would be the ideal solution. Make this in here stable that your core of material does not get washed away. How you do that? That's designers. That's not my issue. You can use geogrids, geotextiles. You can do a reinforcement like a slope reinforcement. You can put containers in again. I don't care about that. But if you thought about that and said, yes, I want to have that, or I don't want to have about that, at least that's the right way to go. Now we come to our huge problem. Because we don't know this over here on this side, how high it's going to be. Well, of course, if I know from history it's going to be at a certain level, I can say, I'll build my dam 2 meters higher. Okay, why not? A lot of money, however. But typically we go just like 1 meter higher than the highest water level we expect. But you can also do something in this occasion, because if this occurs here, there's no chance you can save that levee anymore. You can try to put sandbags in there, forget it, the water's running down, no way to prevent that. But what you can do is you can reinforce this area on the top side with a geogrid, of course. You need a stable foundation. With a stable foundation, when it gets critical, trucks can drive over that. Because if you don't have that and it's wet and trucks drive over it, you get rutting, they can't move forward fast. And then you can put containers on top of that and put your security on top of that and at least prevent this overtopping and save that dam. Because if it's done, if it's gone, it's going to be very, very expensive to repair it. Now we come to the passive wedge. In my opinion, the passive wedge is really a cool design. Because what does it does? As the word said, number one, it's not really a passive wedge number one, it's passive wedge number two. Number one is basically the water collection on the backside. So in case I have an issue that water is seeping through my dam or underneath the dam, I don't want that to happen, because we all know geotechnically what happens if my structure gets wet. It's just going to move and flow away. But if I have a passive wedge on the backside and I have a drainage collection system on the backside with geosynthetics, with gravel material on top of it, and I can take the water pressure away, then I at least have another safety factor in there in case this doesn't work. And additionally, I have my vehicles, which then in an emergency case can drive back and forth, bring sand loads, sandbags, whatever, and reinforce the material or bring this material up. And to prevent an overtopping, there's a lot to it. And in the summertime, the bicyclists and people who walk around can walk on the dam and look at the nice area, and has also an attractive event as well for those people. So here's just the BRAD 16 guideline, or OBOR. I won't go too much in details into that. Very good documents, both of them. They're basically pretty similar with a few changes in there. They basically describe exactly what I just said, like the German BRAD 16 additionally has a beaver protection geosynthetics or meshes up there, because beavers are the ones who really can dig into it, so they have protection in there. They have their passive wedge over there. They have their dike defense road in there. They write about the core. So I'm not going to go into details into that, just showing you that there are values in there, that they talk about the long term. They talk about minimum mass per unit area, about sufficient geosynthetic materials in there, and so on. I'm not going to go into that because I think you can all read about that. Here's something we forgot over the last decades. This is, you can see the number, 2026. This was this year in Germany. Did we ever, I didn't think about that the last 10, 20 years, because it never happened. This January in Germany was, since 25 years, the coldest winter we had. Climate crisis. Yeah, of course, that belongs to it. And this is what happened. Now, this ice, this moves down with a high pressure. It hits your dam or your levee. Does it have an impact, yes or no? I don't know. So they have to investigate everything now and see whether there was an impact against your barrier system or against the structural design of your landfill. Okay, let's come to sustainability a bit. This is just an example, one of the many examples I could show, but this is basically showing you the installation of compacted clay. So I'm looking at a barrier system compacted clay. I'm tired of always explaining this because it's a no-brainer. You have a project, and then you have truckloads. Here, the project size is 4,500 square meters. I took it because it's one container of a GCL. You need 187 trucks to transport the clay on site. Then you have to install them. Okay, I'm not talking about the stress on the access roads. They have to be reinforced as well. They get damaged, the regular roads. You have to storage on site. You have to mix it on site. You have to add water on site. You put in their first layer, 25 centimeters, you compact them, you take it, you water, you put the second layer on top of it, you compact them, you use a vibrating compactor at the end of it, and then you put your cover soil on top of it, and luckily, if it's not hot enough, it didn't dry out, it's in good shape, you install it. There's a lot of equipment out there. There's a lot of CO2 and energy demand and costs involved in that. I know that the contractors hate me on this one, because they have all that equipment there and they want to use their equipment. But we're gone. We're looking in future. We don't have to care about a contractor having his equipment. If it's not suitable with our goals, then we use something else. And the GCL is a bit more easier to install. You can make mistakes. It's a thin element. And I'm a fighter for quality control on site. But you have now one truckload coming to the site. All you have to do is basically deliver it on site, you unroll it, you overlap it. Yeah, you can make mistakes on the overlap. If you don't do that properly, then that's an issue, absolutely. But we're just talking the installation process now, nothing else. And then you put cover soil on top of it. Yes, it can get damaged, you have to be careful. You know, don't tell the contractor, it doesn't matter, you can drive over it. He'll drive over it the whole time. You know, you do have to be on site and look at it. So not only quality control on site, installation is also important to check on site. You have to watch out, because the moment you turn around and walk away, he's going to do everything different. The easiest way for him. And then those things work pretty good. Just very short, it's a summary. I'm not going in details because you hear one more presentation from Henning on that. But this is just 42% less energy demand, compacted clay liner versus GCL. 42% less. And what you see over here is about 15 years old. You all know what the energy prices are right now. That's another crisis. It's just nearly like a climate crisis. But again, the numbers might be different. Same thing, CO2. 60% less CO2 using a GCL for this particular project. You can't take this number for granted for every project. They're all different. As we heard from Mr. Gruber, it's distance. If the geosynthetic has to be transported 800 kilometers, it's different than if the clay only has to be installed 10 kilometers. Those things have to go into it. And then a few projects, I'll go through these very quickly because I think they're all always the same. Here, this installation of a geosynthetic clay liner, unrolling of the geosynthetic clay liner, and now putting the vertical trench in here. That's the Brat 16 version. You don't need that necessarily, but it's the safest. If you can bind this down into the impermeable bottom layer, then you definitely don't have any water flowing under the barrier. This is a Dutch project, I think it was Basel, right? Basel? No. Where's Reich? That's your project, right? Yep, and here it was done horizontal. You can do that because the water has to still flow into that direction, and it's held back for a few years before that happens. And here's just a brief summary of a few things. I spoke about CO2, energy saving. Saving water, I didn't really touch that topic, but again, if you take compacted clay, you have to add water. Water is a resource. We don't have much water. You have to add that. Saving costs is clear. Less transportation vehicles, meaning less damaging. But an important part, which is also one of the UN goals, is less noise emission. If you live in a town and 187 trucks drive through your town instead of just one, that is a UN goal, and it has less impacts to the roads. Drive through Germany, or I heard even in the US, the roads are not in the best condition anymore. Bridges are not in the best condition anymore. We have to reduce that as well. We can do something. So that's basically the end of my presentation. I won't have a conclusion in that. I'm just saying that if you follow this concept, impermeable barrier, if you look at this part over here, so you look at this section over here, you look at this section over here with the reinforcement, and you look at this section over here, if you young engineers do that and design more than what they expect from you, I am happy. You are happy, and the world will be happy. Okay, well, that's maybe a bit too easy now. Okay, well, that's it. Thank you very much. Listening to my Sustainable Resilient Future in Flood Protection.